The Pacific Ocean covers more than 10 million square miles. If you were placed in the middle of it on a small canoe, without a compass, sextant, or GPS, the isolation would be immediately terrifying. For decades, European and American historians looked at this vast expanse and concluded that ancient Pacific Islanders could not have intentionally navigated across it. They favored a theory known as accidental drift. The premise was that the settlement of Oceania was a product of blind luck, people passively floating downwind on ocean currents. Norwegian explorer Thor Heyerdahl became the most famous champion of this view. In 1947, Heyerdahl launched the Kon-Tiki expedition, sailing a wooden raft from South America to Polynesia to prove that early islanders could have simply drifted along with the prevailing currents to find land. This assumption took hold because Western academics were looking for their own tools, like paper maps, heavy metal astrolabes, and magnetic compasses. Because they didn't see these physical instruments, they missed an entirely different scientific framework. Pacific Islanders used maps unlike European charts. This Micronesian stick chart, crafted from coconut ribs and shells, models water behavior, not land. The curved ribs represent ocean swells, and shells mark islands disrupting their flow. It's a tactile data interface. Navigators did not take these charts on voyages. Instead, they studied them on land to build a permanent, multi-layered map entirely inside their minds, a practice known as cognitive cartography. To a master wayfinder, the open ocean is not a blank void. It is a highly structured, readable grid of information. The foundation of this mental map is the star compass, known in Micronesia as the Pafu, and in Hawaii as the Kukulu-Okalani. This diagram shows the geometry of that compass. Unlike a magnetic compass that points to a fixed north, this system places the navigator's canoe at the exact center of the universe. It then divides the 360-degree visual horizon into 32 equal 11.25-degree segments, called houses. The coordinates on this grid are the stars. Because celestial bodies hold fixed positions in the sky year-round, they provide reliable markers as they rise on the eastern horizon and set on the western horizon. A master wayfinder memorizes the specific rising and setting addresses of over 200 distinct stars. As the night progresses, the navigator tracks them from house to house, maintaining a constant rotating X and Y axis in the sky. They calculate latitude by measuring the elevation of specific zenith stars, stars known to pass directly over their destination islands at certain times of the year. By locking onto this celestial geometry, a navigator sets a precise heading and holds a straight line across thousands of miles of open water. But the celestial grid has a critical vulnerability. Heavy cloud cover can completely obscure the night sky for days at a time. When this happens, wayfinders transition to the next layer of the map, the physical topography of the water itself. Out at sea, there is a difference between chaotic, localized waves chopped up by passing winds and deep ocean swells. Swells are generated by distant storms and travel in straight, uniform lines across the ocean for days. Master navigators can physically feel the specific angle of these invisible swell lines hitting the hull of their canoe. By memorizing the swell patterns, they track their exact heading completely blind. The final challenge is making landfall. A low-lying coral atoll is a tiny speck in the ocean, and a canoe can easily sail within a few miles of one and pass right by without anyone seeing it. This diagram illustrates how navigators artificially expand the physical size of an island. They rely on the flight paths of seabirds, like the white tern, which roost on land but fly out over the ocean each day to hunt for food, creating a target radius up to 130 miles wide. By observing a bird flying outbound in the early morning or rushing inbound at sunset, a navigator knows exactly which direction points to land, long before the island ever breaks the horizon. They also look up. The shallow, bright waters of coral lagoons reflect heat and light upward, casting faint green hues onto the undersides of clouds hovering above the atolls. By combining the compass grid, the transit of the stars, the rhythm of the swells, and the habits of wildlife, the wayfinder constructs a highly accurate map out of pure observation. By the mid-20th century, This rigorous scientific system was pushed to the brink of extinction as younger generations increasingly relied on Western compasses and GPS. To save the practice, anthropologists and mariners founded the Polynesian Voyaging Society in 1973. They built the Hokulea, a traditional double-hulled voyaging canoe designed to revitalize the ancient art of wayfinding. They sought out Pius Mau Piailug, a master navigator from the Micronesian island of Satawal. Mau held an unbroken lineage of wayfinding knowledge and agreed to share it. He taught a young Hawaiian named Nainoa Thompson, who adapted Mau's teachings into a hybridized system that grounded the traditional methods in rigorous modern academics. In 1976, guided by Mau, the Hokulea embarked on its maiden voyage. The crew sailed 2,400 miles from Hawaii to Tahiti, relying exclusively on these techniques of cognitive cartography. They arrived on target. This successful landfall systematically dismantled the accidental drift theory, proving once and for all that the settlement of the Pacific was the result of an intentional, precise science. In an era where screens and satellite coordinates often sever our connection to the physical world, traditional wayfinding teaches a profound lesson. If you truly observe your environment, the Earth itself provides all the data you need to navigate.